The survey on fairness-aware recommender systems emphasizes the importance of mitigating unintentional societal and individual impacts due to unfairness in these systems. It highlights the significance of recommender systems in fields like e-commerce, economics, and education, focusing on their potential to generate significant revenue and improve user experiences. The paper delves into the causes and consequences of unfairness, including gender discrimination in job recommendations and geographic imbalance in MOOC course recommendations. It emphasizes the need for fairness-aware systems to address these issues. The survey categorizes current advances in fairness across different recommendation scenarios and introduces methods to promote fairness at various stages of recommender systems. It discusses datasets and evaluation metrics used to assess fairness and explores the influence of fairness-aware systems on real-world industrial applications, highlighting the connection between fairness and trustworthiness. The survey concludes by summarizing key concepts, frameworks, and challenges in developing fairness-aware recommender systems, emphasizing the balance between accuracy and fairness and ties with trustworthiness. Fairness in recommender systems is crucial for developing trustworthy, responsible, and socially beneficial AI services. It benefits users, items, and the systems themselves, and its importance cannot be overstated. This survey focuses on advancements in fairness-aware recommender systems and how fairness intersects with other aspects of trustworthy systems. Existing methods are categorized into pre-processing, in-processing, and post-processing approaches, each with a comprehensive and fine-grained taxonomy. Fairness influences various aspects of trustworthy recommender systems, including explainability, robustness, privacy, and more. The authors highlight the need for fairness in multiple stages of recommender systems, particularly in dynamic user-item interactions, which can perpetuate unfairness if not addressed. To avoid learning and amplifying historical unfairness, fairness must be enhanced at each stage of development. This involves recognizing and mitigating biases in data, algorithms, and user interactions. Fairness-aware recommender systems have significant industrial applications in e-commerce, education, and social activities, aligning with other ethical principles of trustworthy systems, such as transparency, accountability, and non-discrimination. The authors emphasize that fairness is not a one-time consideration, but rather an ongoing process that requires continuous monitoring and adaptation to ensure trustworthy and responsible AI services. By integrating fairness into recommender systems, we can promote more equitable and socially beneficial outcomes, ultimately leading to a more trustworthy AI ecosystem. Fairness-aware recommender systems have emerged as a crucial area of research, aiming to mitigate biases and ensure equitable treatment of users. This survey provides a comprehensive overview of the field, highlighting its significance and future directions. The survey's organizational layout, illustrated in Figure 1, demonstrates the logical connections between each section. The contributions of this survey are threefold. Firstly, it presents a holistic taxonomy of fairness-aware recommender system methods, categorizing them into three phases: pre-processing, in-processing, and post-processing. This framework provides a clear understanding of these methods for researchers. Secondly, the study establishes connections between fairness and other ethical principles, such as explainability and robustness, in trustworthy recommendation systems. Finally, it evaluates existing challenges and future directions, emphasizing the need to address inconsistencies in fairness definitions and the neglect of relationships between fairness and other ethical dimensions. Recommender systems, which learn and predict user interest in items, serve as information filtering systems. The goal is to learn an information filter that captures user preference. The predicted score for the user's preferred item is a critical output. Fairness-aware methods improve fairness in these systems by addressing biases in pre-processing, in-processing, and post-processing phases. The survey highlights the importance of evaluating the impact of promoting fairness on other ethical metrics and identifies existing limitations and challenges, including inconsistent fairness definitions and neglected relationships between fairness and other ethical dimensions. Addressing these challenges is crucial for future works in fairness-aware recommender systems. The concept of fairness in recommender systems is crucial, emphasizing the need for equal treatment of all users and items. The paper categorizes causes of unfairness into data bias, model bias, and feedback bias, highlighting how these biases can lead to undesirable consequences. Data bias arises from training datasets containing user information with potential biases, including user attribute bias and user selection bias. Exposure bias, where users have limited access to the available item set, is also discussed. This sets the stage for a detailed analysis of these biases and their impact on recommender systems. The lifecycle of recommender systems, as depicted in Figure 2, comprises data collection, model learning, and loop phases. Biases in each phase can have an unfair impact on the system, with existing biases potentially amplified in subsequent phases. Time bias occurs when freshly released data overrepresents users' short-term interests, neglecting long-term fairness dynamics. For instance, job recommendations may prioritize new job advertisements over older ones, despite users' long-term career aspirations. Cold start bias arises from a lack of data for new users or items, where prior knowledge from warm start recommendations is used to train cold start recommender systems, introducing biases. Model bias occurs during the model learning phase, where design flaws, such as ranking bias, can magnify biases in the input data. Ranking bias is exacerbated by certain loss functions, like point losses and pairwise losses, which favor popular items over less popular ones, amplifying unfairness in the recommendation ranking list. The paper delves into the concept of fairness in recommender systems, shedding light on various types of biases that can occur. Feedback bias, for instance, arises from the interaction between users and the system, leading to popularity bias where a few items dominate recommendations, resulting in an unbalanced data distribution. In terms of fairness expressions, individual fairness aims to provide similar prediction scores for similar users, while group fairness seeks to ensure equal treatment for protected groups. The paper also discusses static and dynamic fairness, with static fairness focusing on short-term fairness and dynamic fairness considering time bias. Furthermore, the paper touches on single-sided and multi-sided fairness, emphasizing the importance of balancing the interests of multiple stakeholders. Other perspectives of fairness, such as ranking fairness, which ensures statistical equality and sorting, are also mentioned. Fairness-aware recommender systems can be categorized into 3 stages: pre-processing, in-processing, and post-processing. In the pre-processing stage, methods independent of recommendation models, such as data relabeling, data resampling, and data modification, aim to minimize biases in the training datasets. These biases can be amplified throughout the lifecycle of a recommender system, resulting in unfair recommendations for users. In-processing methods focus on improving the fairness of the model from a method perspective, encompassing various techniques like regularization-based methods, causal inference-based methods, adversarial learning-based methods, reinforcement learning-based methods, and ranking optimization-based methods. These methods address biases in the model itself, rather than the data. Post-processing methods treat the model as a black box and solely process the model's output results, employing model-independent methods. These methods include non-parametric re-ranking methods and parametric re-ranking methods, which adjust the output rankings to ensure fairness. Several fairness concepts are discussed, including individual fairness, which requires that similar users receive similar visibility in the ranking; causal fairness, which considers both observational data and additional causal relationships within them; long-term fairness, which considers the long-term impact of fairness interventions; and envy-freeness fairness, which states that each user should prefer their own recommendations over those of other users. Other fairness concepts, such as Rawlsian maximum fairness and maximum shared fairness, are also mentioned. A comprehensive summary of fairness-aware recommendation methods is provided in Table 1, including the biases the methods can address, the types of fairness-aware recommendation methods, and other important information. In the preprocessing stage, fairness-enhancing methods are categorized into 3 types: data relabeling, data resampling, and data modification. Data relabeling methods, such as the self-supervised relabeling framework designed by Wang et al., aim to remove biases in the input data by dynamically generating pseudo-labels for user profiles. This survey categorizes fairness-aware recommender systems based on their implementation phase, technology, bias issues, suggested applications, and method names. Table 1 provides a comprehensive summary of these methods. Preprocessing methods include data relabeling, resampling, and modification. Data relabeling methods, such as IFNA, address popularity bias in general recommender systems. Data resampling methods, including MPML, HPO, ARNS, and HFD, tackle user bias in general recommender systems. Data modification methods, such as HER, CFAI, RSNMF, and EPTB, also address user bias in general recommender systems. In-processing methods involve regularization techniques. For instance, Clover addresses cold start bias in cold start recommender systems, while MinDiff, FRRPC, SERIC, and IDLR tackle exposure bias in social recommender systems. FARL, CPBLR, CFIFD, FFFU, SLIM, PHI-REXIS, MMIUR, F2VAE, FAIR-REC, IURPF, and FRRP address popularity bias and user bias in general recommender systems. Causal inference methods, including Clover, DHRS, ABPUL, IANP, PDA, MACR, Dancer, FAIR-TED, CSBRS, SHT, RTDLE, TPFB, ADA Request, InVPref, DECOVIR, and AIPB, address cold start bias, exposure bias, and popularity bias in various recommender systems. Adversarial learning methods, such as FAIR-REC and FRFC, address user bias in general recommender systems. Reinforcement learning methods, including FCPO and MORL, tackle exposure bias in social recommender systems and popularity bias in conversational recommender systems. Ranking methods, such as RDC and CPR, address exposure bias and popularity bias in social and general recommender systems, respectively. Other methods, including CLREC, SARNet, CUAB, and FAIR-SR, address exposure bias and user bias in session-based, conversational, and social recommender systems, respectively. Post-processing methods involve non-parametric and parametric techniques. Non-parametric methods, such as GEN, CP-FAIR, FAIR-MATCH, and TFROM, address exposure bias in cold start and general recommender systems. Parametric methods, including HyperFair, address exposure bias in general recommender systems. Some specific data modification methods, such as those proposed by Sellis et al. And Dane et al., proportionally subsample the dataset based on sensitive attributes or create data resembling exposure data through feature matching techniques. Wang et al.'s method implements natural language processing preprocessing techniques to modify the training data, addressing noisy data problems in recommender systems. In the realm of fairness-aware recommender systems, in-processing methods are pivotal for mitigating unfairness during model training. These methods can be categorized into 5 distinct categories: regularization-based, causal inference-based, adversarial learning-based, reinforcement learning-based, and ranking methods. Among these, regularization-based methods have emerged as a prevalent approach to promote fairness in recommender systems. This technique involves adding a fairness-related penalty term to the model's loss function, which is the sum of the performance loss and the regularization term. The paper explores different types of regularization terms, including norm-based, matrix-based, and pairwise regularization terms. Norm-based regularization utilizes norms such as the L1 norm and L2 norm to assess the deviation of the model. For instance, Burke et al. Proposed employing L1 norm and L2 norm as regularization terms to reduce multi-sided unfairness issues, like user neighborhoods. Matrix-based regularization terms are also examined, with Abdallahpour et al. Introducing a matrix-based regularizer, LAP-DQ, to reduce popularity bias. The LAP-DQ regularizer is defined as the trace of the product of matrices, aiming to enhance fairness in the recommendation process. This section provides a comprehensive overview of various in-processing methods for fairness-aware recommender systems, highlighting the role of regularization terms in promoting fairness. It offers a detailed examination of different types of regularization terms and their applications in addressing various forms of bias in recommender systems. In the realm of fairness-aware recommender systems, researchers have been grappling with the issue of popularity bias and other forms of unfairness. A causal graph, as depicted in Figure 5, visually represents the intricate relationships between variables in a recommender system, revealing how user history influences both user and item representations, thereby perpetuating popularity bias. To tackle this problem, several regularization methods are proposed. One such approach involves adding a regularizer to the loss function, which penalizes the model for predicting that one group clicked on an item more than another group did. This is achieved through correlation-based regularization, as proposed by Butel et al. 9. Another method is the use of an orthogonality regularizer, which orthogonalizes unbiased user embeddings to biased user embeddings, as proposed by Wu et al. 146. Causal inference methods for fairness are also discussed, aiming to identify and mitigate the sources of bias. These methods can be categorized into inverse propensity scoring, backdoor adjustment, and counterfactual inference. Inverse propensity score methods, such as those proposed by 126, reweight samples to reduce the influence of biased samples, without altering the causal relationship between variables. The authors provide detailed mathematical formulations for these methods, including the correlation-based regularization term, the orthogonality regularization term, and the probability distributions used in inverse propensity scoring. They underscore the importance of addressing unfairness in recommender systems, citing various studies that have proposed different approaches to mitigating bias. Overall, the authors present a comprehensive overview of fairness-aware recommender systems, emphasizing the need for causal inference and regularization methods to address popularity bias and other forms of unfairness. In the realm of recommender systems, fairness-aware methods have emerged as a crucial aspect to mitigate various biases that can skew recommendation results. This section delves into three primary categories: inverse propensity score, backdoor adjustment, and counterfactual inference. The inverse propensity score (IPS) method is designed to estimate the propensity score of a user item pair being recommended. This score is then utilized to reweight the training data, thereby reducing the impact of biases. For example, the propensity framework proposed by 108 estimates the propensity score for enhancing exposure fairness in scenarios with implicit feedback. Backdoor adjustment is another approach that modifies the causal graph of the real world to create a counterfactual world where fairness is ensured. The MACR framework, 143, is highlighted as a representative method, which aims to alleviate popularity bias by adjusting the recommendation interaction matrix. This adjustment is achieved through a transformation of the causal graph, removing the causal relationship between the item's popularity and the recommendation result. Counterfactual inference methods construct a counterfactual causal graph based on the real causal graph, ensuring that the recommendation results in the real and counterfactual worlds are the same. This approach is applied in various contexts, including mitigating popularity bias, 167, improving explainable fairness, 44, and ensuring fairness in personalized recommendations, 75. Lastly, the paper discusses adversarial learning for fairness, which involves a generator and a discriminator. The generator produces node embeddings, while the discriminator predicts sensitive features from these embeddings. Through a min-max game between the two components, the method learns fair representations by passing a negative gradient to predict the sensitive attribute, enabling the generator to learn unbiased representations. In the realm of fairness-aware methods in recommender systems, two distinct approaches have emerged: adversarial learning and reinforcement learning for fairness. Adversarial learning-based fairness-aware methods utilize a generator and sensitive attribute filter to remove sensitive information from user or item representations. This process involves a max-min game between the generator and discriminator, aiming to decouple the output of the generator from sensitive features. Recent studies employing this approach include Clover, which improves the fairness of the cold start problem through metalearning, and Gone, which generates negative signals of users to ensure data fairness. Reinforcement learning for fairness considers dynamic interactions among users, items, and recommender systems as a Markov decision process, MDP. Reinforcement learning methods are used to train recommendation strategies from users' historical information, introducing fairness concerning feedback during the training process. Long-term fairness and dynamic fairness are two typical concepts addressed in this context. focusing on mitigating time bias. For instance, Zhe et al. Propose a fairness-constrained reinforcement learning recommender system that models the recommendation process as a constrained MDP, enforcing population equality and exact K-fairness constraints at all reinforcement learning iterations. This approach enables the model to dynamically adjust the recommendation strategy and guarantee that fairness requirements are always satisfied with environmental changes. The section on fairness-aware recommender systems emphasizes the use of reinforcement learning-based methods and ranking optimization techniques. Specifically, reinforcement learning-based methods strive to balance accuracy and fairness. For instance, FairRec, introduced by Liu et al., dynamically maintains the long-term trade-off between accuracy and fairness by combining user preferences and fairness constraints. Fairness-aware recommender systems have garnered significant attention in recent years, particularly in the context of ranking-based fairness-aware methods and post-processing techniques. Some ranking methods have been shown to analyze the flaws of Bayesian personalized ranking (BPR) loss, achieving unbiased ranking through regularization terms. However, this survey focuses on other niche methods for enhancing fairness in recommender systems. One such approach is the use of contrastive loss, as theoretically demonstrated by Zhou et al. This method replaces the inverse propensity score, reducing exposure bias. In another approach, Shen et al. Propose learning cross-scenario user interests through an attention network, introducing a fairness factor to gauge the importance of each scenario. This allows for a more nuanced understanding of user preferences and promotes fairness in recommendation outcomes. Zheng et al. Take a different approach, designing a context-bias-aware recommendation model that leverages attention networks to infer negative user preferences. This model provides a more comprehensive understanding of user behavior, mitigating bias in the recommendation process. These innovative methods offer promising solutions to the pressing issue of fairness in recommender systems, highlighting the need for continued research in this area. The section delves into various re-ranking methods for fair recommender systems, emphasizing innovative approaches to tackle biases. It commences with a survey of re-ranking methods, including a novel score scaling model and the transformation of recommendation optimization into integer programming problems. Parametric re-ranking methods are also presented, demonstrating their capacity to enhance fairness and equality opportunity-based fairness. The section then transitions to datasets and evaluation metrics commonly utilized in fairness-aware recommender systems, underscoring the significance of employing a diverse range of datasets to identify unfairness and assess fairness-enhancing methods. In the realm of fairness-aware recommender systems, a comprehensive survey is conducted to examine datasets and metrics employed for evaluating fairness. Table 2 provides an overview of selected datasets, including Amazon, Beauty, Opinion, Last.fm, MovieLens, MovieLens 1M, Yahoo R3, and Yelp. Each dataset has unique characteristics and fairness concerns, such as user and item distribution and reference relations. To assess the fairness of these systems, various metrics are utilized. One such metric is the normalized discounted cumulative gain, NDCG, which assigns different degrees of relevance to results, ranking them accordingly and weighting them uniformly. This metric is essential in evaluating the performance of fairness-aware algorithms. Two other key metrics introduced are the Gini coefficient and KL divergence. The Gini coefficient, originally an economic indicator used to measure income inequality, can also be applied to measure the fairness of recommender systems. It calculates the average absolute difference between all possible pairs of exposure frequencies, with smaller values representing greater fairness. KL divergence, on the other hand, computes the divergence between two distributions. It can be used to measure various biases, such as the distribution difference between user history records and popularity in recommendation results, thereby detecting popularity bias. These metrics are crucial in evaluating the fairness of recommender systems, ensuring that they do not perpetuate biases and discrimination. Page 17 of the research paper delves into fairness-aware recommender systems, emphasizing their evaluation metrics and industrial applications. The authors introduce KL divergence as a fairness measure, which quantifies the difference between the predicted distribution and a fair distribution. A lower KL divergence value indicates a fairer system. They also discuss the difference metric, which considers the distance between two recommendation results and a fairness constraint coefficient. If the prediction score of two items is smaller than the fairness constraint coefficient, the system is considered fair. The authors further discuss other evaluation metrics such as prevalence bias, miscalibration, popularity bias, and Hellinger distance. These metrics can be used to assess the fairness of recommender systems in various contexts. The page then transitions to industrial applications of fairness-aware recommender systems, highlighting their impact on real-world scenarios like e-commerce, education, and social activities. In e-commerce, fairness-aware systems can mitigate data bias and contextual bias, ensuring users receive unbiased recommendations. In education, they can ensure users receive fair exposure to different courses and providers. In social activities, such as job recommendations, fairness-aware systems can mitigate discrimination and improve user trust. The authors provide several examples of fairness-aware recommender systems in these domains, including the Scenario-Aware Ranking Network, SAR-Net, for e-commerce, unbiased counterfactual learning for eliminating contextual bias, and fairness-conscious re-ranking methods for education and job recommendations. These examples demonstrate the potential of fairness-aware recommender systems to promote fairness and transparency in various industries. The section on industrial applications of fairness-aware recommender systems highlights various domains such as e-commerce, education, job recommendation, news, and streaming media. It addresses prevalent biases including exposure bias, user bias, popularity bias, and time bias, along with methodological approaches to counteract these biases. In e-commerce, exposure bias is addressed through ranking methods, while user bias is mitigated by re-ranking. Education domain grapples with exposure bias and popularity bias, countered using re-ranking and ranking methods, respectively. Job recommendation systems face exposure bias and user bias, with counterfactual learning and adversarial learning employed to address these issues. News recommendation systems encounter user bias, addressed via regularization and adversarial learning. Popularity bias is also prevalent in this domain, with adversarial learning used to mitigate it. Streaming media recommendations, including music and video recommendations, face time bias, popularity bias, and artist gender bias. Techniques like duration fault quantization, collaborative filtering, and fairness-conscious re-ranking are used to address these biases. The paper emphasizes the importance of fairness awareness in recommender systems to ensure equitable opportunities for all users and content providers. This section delves into the interconnections between fairness and other trustworthy dimensions in recommender systems, including explainability, robustness, and privacy. A trustworthy recommendation system should be open, transparent, and explainable, providing users with understandable results. The authors emphasize the significance of counterfactual reasoning in promoting both explainability and fairness in these systems. In terms of explainability, several approaches are highlighted that can enhance the fairness of recommender systems. For instance, Shui et al.'s counterfactual framework for group fairness offers an explanation for the decision-making process of recommendation models, while Zhang et al.'s explainable weighting method ranks counterfactual recommendation results, providing users with fair and transparent advice. Kernacchia et al.'s model combines natural language processing and counterfactual inferencing to provide recommendations in the loans domain, offering users with fairness and transparent advice. Additionally, Fu et al. Improved the explainability and fairness of the recommender system by designing a fairness-aware ranking algorithm. Regarding robustness, the paper notes that data bias can lead to unfair outcomes and vulnerability to attacks, making the model less robust. To address this issue, Feng et al. Suggest constructing antidote data that mimics the rating behavior of users to mitigate data bias. These data are not considered anomalous data for attacking, thus enhancing the model's robustness. Jin et al. Also explore the connections between fairness and robustness in recommender systems. Overall, this section underscores the interconnectedness of fairness with other trustworthy dimensions, emphasizing the need for a comprehensive approach to ensure that recommender systems are not only fair but also explainable, robust, and protective of user privacy. Fairness-aware recommender systems are categorized into explainability, data modification, privacy, discrimination, diversity, and other methodologies. Explainability methods employ causal inference to analyze the relationship between users' past and future behaviors, alongside counterfactual analysis and explanation to promote fairness. Data modification methods utilize inverse propensity scores to eliminate polarity bias in group recommendations and improve robustness and control fairness through L2 regularization loss. The privacy category emphasizes the importance of protecting user-sensitive information, as recommender systems may contain biased data leading to unfairness. User privacy can be compromised during interactions with the recommender system, even when protected private data attributes are misused. To address this, some works establish a connection between fairness and privacy, such as training risk-free, user-approved private data to make privacy-preserving fair recommendations. Recommender systems may be unfair if users' private information is used extensively for personalization, and when protected private data attributes like gender and ethnicity are misused. User behavior and attributes are found to be correlated in social theory, making it possible to infer a person's privacy from their actions. To address these issues, methods aim to keep user privacy and sensitive information hidden from the recommender system. For instance, Wu et al.'s Fair Go method transforms the fairness-aware recommendation problem into learning fair user and item representations, preventing sensitive information from being revealed from the learned embeddings. This comprehensive survey highlights the connections between fairness-aware recommender systems and trustworthiness properties, emphasizing the importance of protecting user privacy and promoting fairness in recommender systems. Future directions for fairness-aware recommender systems are discussed, highlighting current shortcomings and potential challenges. The need for customized fairness concepts, standardized industry concepts, and balancing fairness with recommendation performance is emphasized. The interaction between fairness and trustworthiness remains underexplored. In the realm of fairness-aware recommender systems, a unified framework is crucial for addressing various fairness issues. The trade-off between fairness and performance, as well as the mutual promotion of fairness and trustworthy properties, has been highlighted. However, there is a lack of comprehensive research on integrating multiple fairness properties, necessitating future works to focus on the interaction between fairness and other trustworthy properties. A table illustrating the current state of research reveals numerous unexplored areas, such as the application of reinforcement learning methodologies for explainability and fairness. Fairness-aware recommender systems are crucial for maintaining trust in recommendation technologies. The paper discusses various scenarios and fairness measurement metrics, emphasizing the importance of fairness in e-commerce, education, and other areas where recommendations have a significant impact on people's lives. It explores the correlation between fairness and trustworthy properties, highlighting the need for novel approaches to ensure fair and trustworthy recommendations. The authors cite studies addressing issues like popularity bias, user unfairness, and the role of deep learning in improving recommendation accuracy and fairness. Strategies to mitigate algorithmic bias in recommendation ranking are also presented. This section delves into the realm of fairness-aware recommender systems, highlighting their diverse applications across various domains. A seminal study on fairness-aware explainable recommendation over knowledge graphs underscores the importance of fairness considerations in system design. 40. The paper also addresses the issue of debiasing career recommendations through neural fair collaborative filtering. 59. Emphasizing the need to rectify potential biases inherent in job advertisement algorithms. Geographic imbalance and provider unfairness are further explored. 58. Alongside the role of reinforcement learning in achieving a Pareto-efficient fairness-utility trade-off in recommendation. 55. Multitask learning with preference graph embeddings is discussed as a means to ensure fairness in sequential recommendation. 71. While a GANS-based fairness-aware learning model for recommendations with implicit feedback is also examined. 72. Fairness metrics, such as sampled metrics for item recommendation. 67. And user-oriented fairness in recommendation. 73, are touched upon. The paper also sheds light on the impact of item popularity bias in music recommender systems, particularly concerning gender disparities. 70. Auditing for discrimination in algorithms delivering job ads. 58. and the challenges and advances in conversational recommender systems, 41, are additional topics of discussion. The survey on fairness-aware recommender systems presents various approaches to mitigate biases in recommendation algorithms. It includes studies on fairness metrics, diversity promotion, and the impact of data sampling on hyperparameter optimization. Researchers have proposed methods based on causal notions, graph-based approaches, and adversarial learning to address biases. The survey emphasizes the need for fairness in music recommendation, news recommendation, and job recommendation, highlighting the importance from both consumer and producer perspectives. Fairness-aware recommender systems are crucial in modern technology, as they strive to eliminate bias and ensure unbiased learning. The importance of fairness in recommendation systems cannot be overstated, as biased systems can perpetuate social injustices and compromise user satisfaction. Debiasing is a critical aspect of fairness-aware recommender systems, aiming to remove discriminatory patterns from data and algorithms. Diversity-aware recommendations also play a vital role, as they promote varied and inclusive suggestions to users. Fairness metrics, such as statistical parity and equal opportunity, are essential in evaluating the performance of these systems. The significance of fairness extends to specific domains, including music and movie recommendations. For instance, fairness-aware music recommender systems can help promote diverse artists and genres, while fairness-aware movie recommender systems can reduce stereotyping and provide more inclusive suggestions. The pursuit of fairness in recommendation systems is driven by the need to address bias and ensure social justice. Biased systems can have far-reaching consequences, including perpetuating stereotypes, reinforcing discriminatory practices, and limiting opportunities for underrepresented groups. By developing fairness-aware recommender systems, we can promote a more equitable and just society. The development of fairness-aware recommender systems is a complex task, requiring a deep understanding of machine learning, data analysis, and social justice. Ongoing research in this area is crucial, as it can inform the development of more effective and unbiased recommendation systems. Page 27 of the research paper presents a comprehensive survey on fairness-aware recommender systems, drawing from 44 research papers and articles published between 2017 and 2022. This section delves into the various methodologies and algorithms employed to ensure fairness in these systems, which are critical for addressing issues such as bias and discrimination. The authors provide an in-depth analysis of different fairness metrics, including statistical parity, demographic parity, and equalized odds. They also discuss various fairness-enhancing techniques, such as pre-processing, in-processing, and post-processing methods. These techniques aim to mitigate bias at different stages of the recommendation process, from data preparation to output adjustment. Moreover, the survey highlights the importance of considering multiple fairness criteria simultaneously, as focusing on one criterion may inadvertently exacerbate others. For instance, improving statistical parity may lead to a decrease in demographic parity. Therefore, researchers must strike a balance between competing fairness objectives. In addition to discussing fairness metrics and enhancing techniques, the authors emphasize the need for more diverse and representative datasets. They argue that current datasets often lack diversity, leading to biased models that perpetuate existing social inequalities. To address this issue, they suggest incorporating additional data sources and applying data augmentation techniques to increase diversity. The paper also touches upon the challenges of evaluating fairness in recommender systems, particularly in terms of scalability and interpretability. As the complexity of fairness-aware algorithms increases, so does the difficulty in understanding their inner workings and assessing their effectiveness across large user bases. Finally, the authors outline future directions for research in this field, including the development of more sophisticated fairness metrics and the integration of fairness considerations into the design of new algorithms. They also call for further exploration of the trade-offs between fairness and other performance metrics, such as accuracy and efficiency.